top of your notes there, I have a simple little statement about pi radians equals 180 degrees. This is just a fact you have to know. I'll spend a lot of today telling you these are things you have to have memorized. There's a lot of things you don't need to memorize. People feel like you have to memorize all of Trig. I swear there's a handful of things I have memorized, but I know how to tie them together. But one of these is you have to have either this fact memorized. Other people have the fact memorized of how far is it all the way around the circle in degrees? 360 degrees all the way around, and then we know that's a full circle. Anybody know what it is for in radians? 2 pi. So if 2 pi is the same as 360, obviously 1 pi is the same as 180, just taking half of that. So this is just a fact you have to know. I'm hoping most of you remember at least this fact, but if not, I just reminded you. My question for you is, if I have this little x and y axis here, where is 180 degrees or pi radians? Did you give me hand signals now?
Second quadrant.
Second quadrant, actually all the way through the second quadrant. No, it's okay, I like the hand signals. So if you start, we always start here. We start on the positive x-axis and measure our angles from there. And so we measure all the way to here. This angle starting here and stopping there would be 180 degrees or pi. So far so good. This angle right here where we start is 0, because if you start there, you haven't gone anywhere yet. 0, over here is pi. What's up here? 90 degrees if you're in degrees. In radians, it would be pi over 2. If you think about it, if this is pi, that's halfway. The big thing in calculus is a lot of us feel more comfortable with degrees, and that's how you first learn trigs. Like, oh, I know 45 degrees and 30, 60s, which is good. But in calculus, everything's in radians because it's actually a measurement. So we're going to start today by converting some radians to degrees, and then pretty much the rest of today is all going to be in radians. You eventually want to get to the point where you can think in radians. Kind of like if, maybe you learned the American metric system, or American system, and you measured everything in inches and feet. But if you moved to Europe, you would eventually start thinking in the metric system, just because that's the way it all works there. So even though you were comfortable with what you learned, if you're comfortable with degrees, you want to get to the point where you can think in radians. And I'm going to show you how to easily convert so you can start thinking that way better. Okay, so we're here so far? That's the basics to start with. Okay. So what I want to do is just take these first few examples on my list and just convert them from either radians to degrees or vice versa. So we already talked about that one. 2 pi is 360 all the way around. That one was easy. I'm going to talk about quick ways to do this too. The next one is 60 degrees. Some people who already do what I call think in radians already know what 60 degrees is in radians. Who knows?
1/3 pi.
He already knows it's 1/3 pi. Some people know it's pi over 3. If you don't know it, that's part of what today's for. If you don't know it, you just have to know this fact. 60 degrees, let's compare it to 180. That's the same as 180, oops, I lost a 0, over 3. But what's 180? 180 is pi, so that must be pi over 3. So when you hand me an angle, at this point in my life, I think in radians already. I know that pi over 3 is 60, because you do it enough times, you memorize it. But if you hand me an angle that I don't know, I always just try to compare it to how does it compare to 180? Because I know I can replace any 180 with a pi.
And the reason why you divided by 3 is
Because 60 is equal to 180 over 3. I was just comparing this number to 180. So I was thinking, what do you do to 180 to get 60? I have to divide it by 3. Thank you for asking that. Still feeling smart? This way it works, right? We start off feeling smart, and okay, when does it get hard? Okay, so C is pi over 4. In this case, I want to change it back to degrees. Again, some people have it memorized, but using this, what do you think I'm going to do? Change the pi back to a 180 now. Just always change your pi's into 180s or vice versa. So So pi over 4 is 180 over 4. I'm assuming you know how to divide. Turns out to be 45 degrees. So if you convert them back and forth enough, you will memorize that pi over 4 is 45 degrees and pi over 3 is 60 degrees. But if you can't remember, just know how to switch from pi to 180 and do that little division. So what about the last one?
180 over 6.
180 over 6, she says. We have pi over 6. We're going to make that 180 over 6. Do the division. 30 degrees. First line's looking good. Maybe we don't need the trig review. So I'm going to point something out here that
It's the whole first quadrant.
it's all the first quadrant, yes. And I like what you said, it's the whole first quadrant. There's actually a whole bunch of other angles in the first quadrant. You know, there's like the 70-degree angle and the 22 angle. But these angles here, 30, 45, and 60, are the ones that show up most often because there's actually exact answers to those, which we're going to talk about here in a second. You very rarely will ask someone, you very rarely will see a problem that says, hey, find the sine of pi over 7. You can find it with a calculator and turn it into a decimal, but what we're doing today, actually, I'm never going to touch a calculator. We're going to do everything exact answers, which is a lot, you know, calculus always wants a nice exact answer with square root of 3 over 2 times pi or whatever. So everything today, I'm going to use what we call the special angles, which are 30, 45, and 60, as well as multiples of 90. So good? We got those? Okay, so speaking of special triangles, that's what I have next. So I'm going to put the colors around here so I don't forget. This is one thing that I said you have to memorize. You just have to know that. And you all agree that if you know this, you could figure all those out. So you don't have to think in radians, but you have to be able to convert. Okay, so that's one thing you have to memorize. The next two things you have to memorize are these two special triangles. They didn't print very well on my page. Hopefully you can read them. And this is a right triangle with a pi over 4. Good morning.
Good morning.
What did we just say pi over 4 was? 45-degree angle. So a lot of people think of this special triangle. I'm going to redraw it underneath. It's really not any different. If I could draw it better at the end. Uh-oh, looks like my pen's not going to erase it. I'm going to go bad. A lot of people call this special triangle the 45, 45, 90 triangle. Guys, we're just starting on the special triangle. So what makes it special is that it comes up quite a bit, but also the two sides have to be the same size because of the angles being the same size. And we usually label it as 1 and 1 and square root of 2. Where's the square root of 2 come from? Pythagorean theorem. 1 squared plus 1 squared adds up to 2. So this has to be square root of 2 squared. So that's where the Pythagorean theorem. And we label it 1, 1 square root of 2, but it could have been, I'm going to write it here in red to erase it. It could have been that this was 5, and this was 5, and this was 5 square root of 2. It's just that those are the ratios. These two have to be the same, and this is square root of 2 times whatever those were. So this is, we use 1, 1 square root of 2 just to show the ratios, but they could be anything as long as they have that same relationship. Okay, so we have to memorize that one. I think it's pretty easy to memorize because you know the x's and the y's are the same, and then you can use the Pythagorean theorem if you forget the square root of 2. But this is, as I was saying, this one thing you have to have memorized. This is another one you have to have memorized. And I, of course, am going to call it this one because it has radians in it. Because remember, I said everything in calculus is in radians, so we might as well think in radians. But we agree it's the same triangle. For those of you who just came in, I was just starting off saying that there's certain facts that you have to memorize, and then from those facts you can figure out the other stuff. So these things I'm putting in double boxes with green and black are the things that you definitely have to memorize at some point. But there's really not that much to memorize, which is my point today. Questions about that triangle? We've seen that, feel good about it? What are you gonna say? Okay, so the other one? Pass that back to him afterwards. Thank you. The other one is, I wanna make sure I draw it the same way. This guy. Pretend my pictures have straight perfect angles. This is pi over 6, this is pi over 3, and the relationship here is not as obvious. We would have to spend more time than a quick 2-hour trig discussion as to why it's 1, 2 square root of 3. But what are the angles in here in degrees?
30 and 60.
30 and 60, so a lot of people will talk about the 30, 60, 90 triangle. Again, I'm just starting off hitting you hard with the radians. This is a 30, that's a 60 that we just talked about, and a 90. The relationship on that special triangle is always, and I always draw it if I'm freehanding it, I make a point to make sure that one angle definitely looks smaller than the other one. Some people will real quickly draw a triangle on their paper, but if it looks too much like this, it's hard to tell which one's the 30 and which one's the 60. So if I'm freehanding and doing something real quick, sometimes I'll even exaggerate. I mean, I don't care if it's not exactly 30, 60, but I need to see that that's the small one and that's the big one. And so this is not technically accurate in terms of which one is which, but if I'm trying to draw a 30, 60, 90, I know that the relationship would be this. And the relationship is always that if you call the shortest side 1, the hypotenuse is double that. The hypotenuse, not the other side, the hypotenuse is double that. And then from the Pythagorean theorem, again, you get the square root of 3. I was just talking to someone last week who said, I never can remember which one goes where, the 2 and the square root of 3. I can't remember. So let's say that this was you, and you're like, oh, I don't remember which one was which. Maybe the 2 goes here, and the square root of 3 goes here. This is not correct. But if you're thinking that, how can you check to see if you're right? If you're trying to memorize this, you're like, do I remember it right? How can I?
Do the Pythagorean.
You could check the Pythagorean theorem. 1 squared plus 2 squared equals square root of 3 squared. Uh-oh, I got 5 equals 3. So that tells you you've got it wrong. So quick, switch them back, okay? A lot of times for me, instead of memorize everything, if you know part of it, try it, check it. If it doesn't work, put it back. Another way is you could put this into your calculator. It's like 1.7-ish. This is the longest side. How can 1.7 be more than 2? Either way, I've got them backwards, so now I set it up wrong. So even if you don't have it completely memorized, you can check if you're doubting yourself whether or not you've got it right. But once you have these 2 triangles memorized, you can pretty much do everything we need to do for 90% of what you're doing in trig. You have to have them memorized though. We good there? Okay, Zach. So, I have that other triangle next to it. Let me pass that back, please. Thank you. And I just put it here on purpose so that we would have to fill it in ourselves. This one's a right angle. Which one's the 30? Which one's the 60? 30 is the top one because it's the smaller one. Notice I even call it the 30, but then I write pi over 6. Unfortunately for me, it's a habit that I can say, you could say a dozen and I could say 12, and we were saying the same thing, and I just interchanged them, right? So pi over 6 is the same as 30. You want to get to the point where you can remember that. Again, if you don't remember, that's a pi. You can always go back to this and figure out which one is which. If you forget, just go back and it takes all of 4 seconds to divide 180 by something to see which one it is. So if this is the case here, which side is the 1?
On the bottom.
On the bottom. The shortest one is always the 1. The hypotenuse is always the 2. And the other side is square root of 3. So far so good? The first page is the only easy page. Okay, actually a lot of it's easy once you know trig. But the first page, I'm assuming for most of you who are here because you don't remember your trig, are okay, I remember this isn't so bad. The first page is usually where people feel good, and then it's when we start throwing in all the sines and the cosines and the cosecants and all this other stuff that all of a sudden your brain freezes up. We're getting there. Okay, so on the bottom I just want to draw some angles to make sure we know how to find them. Because if you can't find an angle when you draw it, you can't really find anything else out about it. So if I want to draw a 225-degree angle, this is example 2. Somebody try to describe to me how to do that.
Be like 180 plus 45.
Ooh, I like what he said. Did you guys hear that? He said, that's 180 plus 45. That's exactly the way I think of it too. Because we know where 180 is. 180 is from here to here. Plus another 45. Where's 45?
Halfway.
Halfway, because this is 90 degrees, so halfway in here. I'm gonna grab another color here. So if I start here, all the way to here, halfway, that would be a 225-degree angle. Put it right here. 180. I always break things up into multiples of 180 or multiples of pi and add or subtract from there if you need to. Okay, with that one, that should be halfway. My drawing's not totally accurate, so make sure it's clear if you can't tell. My little lines get lopsided. Okay, but now the next three are all in radians, which gets a little bit trickier for us to think that way, but we're gonna get there. So for B, I have 2 pi over 3. Oh, I just scribbled over my B. 2 pi over 3. There's a couple different techniques on how to find it.
Would you plug in 180 for pi and then divide it?
Okay, so that's one way right there, is turn it into degrees. So that's why I said there's a couple different techniques. Some people think better in degrees. If you think better in degrees, change it to degrees. 2 times 180 over 3, I think it turns out to be 120. And if we look at it that way, let's just finish doing it this way. If we look at it as 120, how are we going to find 120?
90 plus 30.
Say that again?
90 plus 30.
90 plus 30. Why does she want to do 90 plus 30?
You know where 90 is.
We know where 90 is. I mean, that's really what it is. Take what you know and build from that. So if we start, am I too far in the corner, Nick? No? Okay, good. I realized I promised I wouldn't go in the corner, and here I am. If we start here and we go to 90, we have to go 30 more. Now 30 more from there is how far?
Pi there. Pi 6. Pi 6. Pi over 6.
Yeah, it's pi over 6, but like how far, when I'm visualizing how far to go, that's the question. Less than halfway, he says, right? Because we're only going, this whole thing is 90, right? Just this from here to here is 90. We just want to go 1/3 of that. So again, just kind of eyeball it, draw it in thirds. Maybe it's roughly about here, right? Where that's 30 and that one would be 60. As long as you're less than halfway, I think it's accurate enough in terms of a drawing. So this is 2 pi over 3. That's if we change it into degrees. I will recommend that you practice getting to the point where you don't need to change the degrees every time. It works. I have no problem with somebody getting there and taking the longest route to get there as long as you get there. But if you practice thinking in radians, it's just quicker to draw it. What I do when I see 2 pi over 3, I can do it 2 different ways. Sometimes I think of it as pi over 3 plus pi over 3. Just in my head, that's kind of the way I think of it, 2 pi over 3s. So pi over 3 is 60, that's roughly about here. And then if I add another 60, I'll end up over here. But sometimes I also think of it as this way. I know that pi is 3 pi over 3. Pi is all the way here. Subtract 1 pi over 3. So 2 pi over 3 is pi minus pi over 3. And to me, that's the easiest way to visualize it. I go all the way to pi, And then I'm backing up by 60 degrees. There's a little 60 degrees in here, or pi over 3 if you're doing radians. So I just kind of look for the closest thing and then back up so I know what this angle in here is, which in a minute will be the one that we care about anyhow. All of those are the same way to get there. You just need to figure out which one works for you. Questions on that one?
Or just 2/3 of pi, which is this.
Exactly, or 2/3 of pi. Like I said, there's so many different ways to do it. He's like, okay, this is pi. If you imagine, if you just take a straight line, visualize dividing it into 3 equal pieces. There's 1, there's 2, right? Same thing. It's all how you look at it. So again, I don't care how you get there, just as long as you can get there. Because when I ask you in a few minutes to find the sign of 2 pi over 3, if you don't know where 2 pi over 3 is, the sign's going to be a little more challenging. Okay, that was B. What's my next one? 7 pi over 4. 7 pi over 4. Let's try it without switching to degrees, since we're going to practice working in radians. I will take recommendations on how to find it, thinking in radians.
Pi minus 1/4.
Ooh, I like it. So it was 7 pi over 4, and he says that's 2 pi minus pi over 4. How did he know that? What did he do in his head? Or maybe he wrote it down, I don't know. How did he know that? He's just a genius.
He rounded it to 8 pi on 4.
Exactly. He thinks about 2 pi. If we're talking about fourths, we're really saying 2 pi is 8 pi over 4. And again, we know where 2 pi is. We know where 2 pi is. So that's 8 pi over 4, and we just need to subtract 1 off to get to 7 pi over 4. That's the easiest way, I think, to draw this one. So I'm going to go all the way around the 2 pi, and then back by pi over 4, which is 45 degrees again, halfway through there. That's the easiest way. I'll show you my other way too, though. So if we start here, we go all the way around to here, which should be halfway. That's 7 pi over 4. What's this little angle in here? This little guy right here. 45. What is he in radians though? We're thinking radians, remember? Pi over 4? Right, that's the one we subtracted off. We went all the way around and subtracted that off. You don't really need this right now. We will in a little bit though. That's a little pi over 4 left in there. So we can find angles? Yes, Joe?
Could you start with the first reference angle, like you said, pi over 4, and then count 7 times around?
Exactly, that's the other way I do it. So I often count by whatever what he calls the reference angle. So he's saying this is 7 times pi over 4. So here's, starting from here, here's 1 pi over 4. 1, 2, 3, 4, 5, 6, halfway down, 7. See how I did that? Yes.
Can you just know that 7 pi over 4 is there because of the unit circle?
If you know the unit circle, right, that's my whole point. I don't care if you visualize the unit circle. Some people memorize the unit circle. My goal for today is no one has to memorize the unit circle. Some people have, and that's great. But the point is, if you can find it without memorizing, because a lot of people are like, that's just too much to cram into my brain. But if you know it, fine. But I'm giving people techniques on how to find it if they don't. But you're right, that's where it is in the unit circle. I personally don't have the unit circle memorized, and I've been doing calculus for longer than all of you probably have been alive, maybe not combined. But I don't. I mean, maybe I only have to hesitate a few seconds to tell you where 7 pi over 4 is, but I can't just point at it. I don't know where it is. But I can think, really in my head, I do what Malik said, and I visualize this, and I know it's here after thinking. But I'm a big proponent of only memorizing the small facts you need to have and use them to get the other ones. Eventually you end up with other ones memorized. Kind of like the way that I say I just think in radians now. I've done it enough. But my point for today is to try to get you all to get to that point where you can figure stuff out without having to go, it's Trig, I don't remember anything. So even if you have nothing memorized, I'll give you just a few things to memorize so far today. Do I have one more example? That was C? I have one more. What's my last one? Ooh, negative 3 pi over 4. Let's throw a negative one in there. What do we do when it's negative?
Go the other way.
Go the other way. Instead of going counterclockwise, we go clockwise. I think maybe I'll use Joe's technique to find that one. So if we start here, we're going negative, so this is 1 pi over 4, 2 pi over 4, 3 pi over 4. So we end up over here. We actually rotate this way. Feels all right? Okay, here on the next page is where some people start to get lost.
What's the other way to do that?
Another way to do it would, again, I would think of negative pi, going all the way to pi, and then back up by another pi over 4. Because this is 4 pi over 4 plus that pi over 4. Go all the way to here, and then back up by a pi over 4. Or change it to degrees. There's about four different ways to get there.
So you would do negative 180 plus pi over 4?
Right, so I'd go all the way to negative 180, if I'm doing degrees, and then realize, wait, now I have to go forward again, so I have to go positive 45, because remember that direction. Another way to think of it is just take the whole negative out of it. Pi minus pi over 4. Some people think of it as like I'm going in reverse. Pi and then backing up by pi over 4, but in the negative direction. That works as well. Okay, so the top of the second page there has the 6 trig ratios, and they're defined there in that box. And I have to tell you that depending on when you learn trig, where you learn trig, who taught you trig, which book you use, there's different definitions of what sine is, what cosine is. Some of you already know SOHCAHTOA, which I'll mention a little bit later. I have to tell you, I didn't learn SOHCAHTOA until I was about, I don't know, I might have been 40, but I'm a lot older than that now. But, I mean, I had already gotten my degrees in math, I got 2 degrees in math, I'd been teaching here for about 15 years, and someone told me SOHCAHTOA, I'm like, what's SOHCAHTOA? I actually know all this trig, and I never learned SOHCAHTOA. We'll go back to what SOHCAHTOA is later, but I think most of you know that. It's one tool that helps, but it's actually not the definition, which is why I'm going with the definitions. And some people learn unit circle first, but then they try to memorize the unit circle. And I'm like, I can't handle the unit circle, I can only handle 2 triangles, which is what the point is of today. Okay, so look at the SOHCAHTOA a little bit. So at the top there, I'm going to squeeze these up in the upper left-hand corner. You have them here to refer to for the rest of today. But these are the definitions. When you have some point, like in that picture, which I'll draw here in a second, I'll put these in the same order. Oh, I just wrote that backwards. Can't read my own writing. When you have some point, I'm going to draw a picture of it in a second here. These are the definitions. Write them. This is when you have any point, I don't care where it is, some point right here, which has an x and a y. So you just found the point like in algebra where you said plot the point x, y. If you draw a line to it, this r is the radius, if you thought of it, if it was a circle, but they just call that r. That could be a hypotenuse if you're talking about a triangle. The definition of the trig functions is that if you want the sine at this point, just take the y value over that distance. That's the definition. If you want the cosine, take the x value over that distance. Notice there's no triangle here yet. There will be. And then the tangent is the y over the x. I claim that you just need to memorize these 3 things. These first 3. And the way I've always remembered them since 1980-ish is that sine and y have the same vowel sound in the middle. Sine and y, they sound the same. Those are the ones that go together. And then the cosine and the x don't sound alike at all, but that's okay. These guys rhyme in a way. I'm not an English person, obviously. And these ones don't. And then the tangent is always the y over the x. Just kind of memorize that one. So if you remember these 3 definitions, you can find the sine of 7 pi over 3 here in a minute, easily, just with that little definition. You don't need to know SOHCAHTOA, you just need to know these three definitions. And then these three over here are the reciprocal relationships. These are the reciprocals. The first one's reciprocal of that, vice versa, and so forth. The way that I remember those, again, I like to memorize small little bits. I know the tangent and cotangent go together. I got that down. They sound the same. They just flip each other over. We're good. The way I remembered which one here goes with which is I'm looking for the opposite. Right? The opposite, I'm flipping it over. So this is an S. This one better start with the opposite letter. It can't start with another S. That's not the opposite. Because this starts with an S, that starts with a C. This starts with an S, that starts with a C. I mean, whatever tricks you need to kind of remember certain relationships, take that trick and run with it. To me, it's, oh, I'm looking for the opposite, which is really the reciprocal, which means I better have the opposite letter. So I don't really totally have cosecant memorized as it's the R over the Y. I don't have that memorized in my head, but I know it's the opposite of the sine, so then I know to flip that one over. So these, again, you technically need to memorize, but I claim you only memorize the first three and then which ones match up to the other ones. So this is in my memorizing category here. New definitions. You may not remember those definitions from how you learn trig, but it'll help you just remember these little ones. Okay. Given that, let's do some examples. Example 3, we want to find the exact trig ratio for the angle that results from the point 4, negative 5. Red doesn't want to erase. So I'm going to draw the point 4, negative 5. Or negative 5. My scale's not so great, but we get the idea. 4, negative 5, just like from algebra. And the question wants me to find all of my 6 trig ratios. So number 1, it says the angle that results from it. Well, I have to have a line going to it to find the angle. So I'm just drawing a line. This right here is going to be my R. I have an X, and I have a Y, and I have an R. We'll talk about what R is in a minute. What angle am I talking about?
Start from the reference.
We actually don't know what the angle is. I was just saying, well, we could start here and say it's this angle. It could have been that angle. What other angle might I have been talking about? Just kidding. The little one, right? And maybe I was going backwards. Maybe it's this angle. Maybe I went around 47 times and then stopped here. I don't know what that angle is. I'd have to figure that out, but it's pretty big. Everyone agree? We don't really know what the angle is, but no matter what the angle was, it ended up stopping right here at this end point.
So then we just list the ones that are similar?
So we're not looking for the angle actually. We're just looking for the sine. Let's just call the angle theta. We don't really know which one it is. Theta is the angle, might be this angle, might be that angle. Theta is the angle. There's an infinite number it could have been. The one we technically use is what we call the reference angle. It's the one that it makes with the x-axis. That's the one that's going to help us the most, but really it could have been the one that went around 47 times and then stopped. But we do care about the one that it makes with the x-axis.
So how come you said it's necessarily a sine? How come it couldn't have been a cosine?
Oh, I want all of them. The directions want all 6 of them.
Oh,
And all 6 trig ratios. Right, is that what it says?
no, that's why the exact trigonometric ratios.
yeah.
Okay. I didn't see it.
Sorry, it implies all 6 of them, sorry. All 6 of them. If it wants all of them, we're going to find them all quickly once we understand what we're doing. What do I need to find these?
Radius.
The radius, or the R. Yeah, we call it a radius even though it's not a circle, but it is a radius. You can make it into a circle, right? How am I going to find it? Pythagorean theorem is your best friend. Because I'm going to now create a triangle that's not really here, but it is. I'm going to just drop straight down from here, and I've made a triangle. How far is it from here to there? This distance right here is 4. Oh, look, big surprise. How far is it from here to here? It's technically down 5, but if we're just talking about the distance here is 5. Let's go ahead and call it -5 since we went down. You could have put +5, it won't make a difference. So if I have a right triangle right here, and I'm trying to solve for r, Pythagorean theorem's our best friend. 4 squared plus -5 or +5 equals r squared. Yeah? 16 plus 25 equals r squared. 41? So what's r?
Square root of square.
Square root of 41. By the way, the r value is always positive. Even though the x was positive and the y was negative, r is always positive. Because you can't really talk about is it up or down or right or left, because it looks like it's up. So now that we know r is square root of 41, as long as we have an x, a y, or an r, I can do all of these. So the sign is -5 over root 41. If you want to practice rationalizing denominators, we'll do that later. Right now, just go ahead and leave it like this. I'm more worried about the trig than the algebra right now. Okay with that? Just took the y over the r. The cosine is the x over the r. As long as you've got the definitions, we're good. The tangent is the y over the x. Pause for a minute. Anybody questioning where that came from?
No, but the theta, in the unit circle. Yeah, so that's the angle that you're looking for, or what is that?
That's the angle that this point made with the x-axis. And I'm trying to find the sine of that angle, the cosine of that angle. I'm not looking for the actual angle, I'm just trying to find the values of the trig function. At this point, I don't care what the angle is. I just want to know what's the sine of that angle. Yeah, that's it.
Is there times that like SOHCAHTOA is not the same as that?
No, it's the same.
Always.
Yeah. The only time SOHCAHTOA doesn't help is if you land on a 0 or a pi over 2 or a 180, because then you don't have a triangle. That's when SOHCAHTOA fails. I don't know if I have an example, I'll have to make sure I do one if I don't. Yeah, if you don't have a triangle, if your theta lands on one of the axes, there's no triangle anymore, and then SOHCAHTOA does fail. Which is why I never do SOHCAHTOA for years. I understand what it does, but we'll get to SOHCAHTOA a little bit. Other questions here? Did I answer yours? So what am I going to do to quickly get these? Flip them over. Square root of 41 over -5, square root of 41 over 4, 4 over -5. Doable. As long as you memorize the little definition. The y gives you the sine, the x gives you the cosine, tangent's the y over the x. Okay, next one doesn't give me a point, it gives me an angle. 2 pi over 3. Oh, do I still have that picture drawn? I do. Let's squeeze over there, it's already here. Oh, you guys want to draw it anyhow, never mind, we'll draw it anyway. You got it on your notes, we'll pick a new one. We already talked about how to find 2 pi over 3. It was roughly right here. All right, 2 pi over 3. And some of you are going, but wait, Jill, I need to know what that point is. If you're going to make me use your new definitions, Jill, I want to know what that point is. What's this point right here, right? How am I going to find it?
Do a triangle.
Go ahead, what you're saying?
You would take sine of that angle and look backwards.
Well, we're trying to find the sine of that angle. So that's the whole thing. Like how, if we're going to use this definition and take the y over the r, the question is how do I find what the x and the y even are right here?
Draw a triangle, and the angle will be like sine of theta is like opposite.
Okay, So, yeah, he's using so good, but his right, the first part, we want to make a triangle. So once you draw this angle, always drop to the x-axis to make your angle. I'm going to drop to the x-axis to make my triangle. Get that? Are you stretching?
So, and I was just gonna say, if you find out what the angles are, then you know which triangle it is.
Exactly.
That's how you find your x.
Exactly. If you ask me, you walk up to me on the street, you see me this weekend, I'm at the movies or whatever, you say, hey Jill, what's the sign of 2 pi over 3? I don't know the answer. I have to stop and visualize this in my head, and then tie it into these triangles that I know. And then I can tell you the answer. It won't take me very long. I can probably do it in less than 10 seconds. Not when I'm talking about something else, but the point is, I don't want you to memorize the sign of 2 pi over 3. I don't want you to have to look at a little fold out that gives you all the answers to all the trig functions. I want you to be able to figure it out on your own. So the first thing is, draw this. We already talked about how this little angle in here was going to be a pi over 3 reference angle when we drew it over there the first time. So once you realize that, if this is pi over 3, this is pi over 6, what's the relationship between those 3 sides?
36.
It's 30, 60, 90. You know about the sides though.
1, 2.
1, 2, square root of 3. That's the thing, remember, this is the thing you have to memorize. You have that triangle memorized. Which side is 1?
The short one.
The short one. And the 2 goes
The
hypotenuse. And the square root of 3 is the other side. Pause. I need to add something else in here because I'm over here in the second quadrant.
-1.
Aha, the x is actually a -1. I moved left 1. This is technically a -1 because I went left 1 and then I went up. Because I went up, the y is still positive. You guys following why it's a -1 there? If you really want to label this point now, this is the point, -1 square root of 3. The x and the y. Now that we have that, did I ask for all 6 here also?
Yeah.
Okay.
So you would never include the hypotenuse as one of the point value, like you wouldn't say that would be your y. It would always be the straight line.
Right, it's just the point, the x and the y give you the point. Because when you go to do the ratio, that's where the hypotenuse comes in.
Right.
So now that I'm here, if I want to do the sine, I'm going to take the y value over the hypotenuse, the y over the r.
Oh, right. Okay, that makes sense.
I like it, the light bulb went on over your head. So that's just the thing, a lot of people who learn the unit circle and memorize the unit circle, like learn to divide by the hypotenuse up here and make everything into the ugly fractions up here. That's too much for me. I don't want to carry all those fractions around. I'll do the fractions when I get here. I actually, eventually, hopefully you can get there too, I even stop writing this eventually because I can see that this is x and this is y, so I don't need to write it again up there because I can just say, oh, it's the y value, because the y is the vertical and the x is the horizontal. So there's the sine. The cosine then will be
-1/2.
-1/2. The x over the r. The tangent will be square root of 3 over -1, which would probably get simplified to negative square root of 3. So my whole point is, find where the angle is, recognize which triangle you have, label your sides, and then you can answer any question you want. What's the sine, what's the cosine, what's the tangent? And then to find the other ones, we will just flip them over. Secant. I'm just going to call that -2. You okay with that? Flip these guys over.
For tangent, that's negative square root 3, right?
Yeah, sorry, my negative and my square root run together. I have a hard time grading people's work too, because some people, when they write square roots, I'm exaggerating, put this really long thing. And so if you make a really long tail out front, the negatives get lost. So thank you for clarifying. It's negative square root of 3. I tend not to put that little line in front for that very reason. But some people put it on there and I can't read it. Is your negative there or not? Or are you losing? So I know it's a change for some of you. Some of you learned to memorize the unit circle. Hey, if you've got it memorized, your life is good. It's just, 10 years from now, is it still gonna be memorized up there? I don't know. For me, it wouldn't. I memorize small pieces and I put them back together when I need to. We got that one? Okay, let's do example 5. Example 5 says the cosine of beta is 2/5, and pi is less than beta is less than 2 pi. Find the values, bless you, of the 5 other trig functions of beta. Oh, this one got a lot harder all of a sudden. What should I do first?
Did you have your X and your R already, or?
I have my x and my r already, so that's helpful.
You plug it in and then you Pythagorean theorem
Plug it in and use Pythagorean theorem. Plug it in where?
into the triangle.
Okay, so the first thing I want to do is draw that triangle. Exactly. So I want to try to figure out where's my angle in the first place. So the cosine is 2/5. What's the other restriction? Between pi and 2 pi. What does that mean? It's either quadrant 3 or 4. It has to be here or here, right? From between pi and 2 pi. How do I decide which one I have? Is it here or is it here? Where do I draw it?
Because, which is it positive or negative?
Right, so my cosine is positive. Cosine of beta was positive 2/5, which tells me what about my x? X is the 2, right? X is positive. If x is positive, I no longer I can't speak. I no longer have a choice as to where to draw this, right?
Can we also use the trick of the quadrants? Like
The all students take calculus?
Yeah,
Yes,
okay.
that and SOHCAHTOA, I learned much later in my career. They work, and for me, it's just like the x is positive, I have to be over here.
Yeah.
SOHCAHTOA works too. To me, I don't like to add in more layers of things to memorize. If it works for you though, I'm not telling you not to use it. I'm trying to stick to the basics today though, just so like, even if you don't remember how that trick works, you know where positive x's are, right? So I like to stick with what we know. So if it's a positive 2, I have to be at the right, but I'm supposed to be in one of these 2 quadrants, so I must be down here somewhere. And I'm gonna make this a triangle. This is a positive 2, and this has to be a 5.
How did we get the 5?
Aha. Because we're eventually gonna remember that the cosine is always the x value over the radius.
Right, okay.
I'm glad you're asking them. You okay with that? 2 over the 5?
And the R is always positive.
R is always positive. And everyone understand why it has to be the 4th quadrant? Because I had to be 3 or 4, but a positive x forced me into 3. Bless you. What do I need now? That's what Caitlin was saying a minute ago.
The Pythagorean.
Pythagorean theorem, so I can find out what this y value is. 2 squared plus y squared equals 5 squared. Four plus y squared equals 25. Y squared equals 21. What's y? Ooh, you're so close.
Negative.
Aha, why is it negative square root of 21?
4th quadrant.
Say again?
Because it's in the 4th quadrant.
Because I'm in the 4th quadrant. This is a y value going down over here, right? If I'm going down, this has to be a negative square root of 21. I like to draw the point, picture what quadrant I'm in. Oh, my x has to be positive, my y has to be negative if I'm over here, because I'm going down. If it was up, it'd be positive. Questions on how I filled that in? So now we want the other trig ratios. So we want the sine of beta. Yes.
How would you know to set it up like that and not have like 2 squared plus 5 squared equals 4 squared?
Because the Pythagorean theorem, when it says a squared plus b squared equals c squared, is referring to a right triangle where c is always the hypotenuse. And these two could be A and B or A and B. Those two legs don't matter, but the hypotenuse is always the c squared. So the hypotenuse in our case is always this one over here, because this is my right angle.
So you always have set up equal to the hypotenuse.
Yes. Yes.
So that point at the end of your triangle would be 2, negative root 21?
Yep. There's my point. Again, I kind of just got sloppy and didn't even write it because technically it's already in my triangle, but if you want to label it, please do. But I always just kind of say this is my x and this is my y, so I don't have to label as much.
I was
Because I
trying
am
to-
a little lazy.
I was trying to remember signs for the fourth quadrant. It's positive, negative, right? Okay.
Well, and again, if you don't, instead of trying to memorize the signs, just say, okay, if I'm going this way on the x-axis, I'm going in the positive direction.
Going down.
And if I'm going down on the y-axis, I mean, go back to the basics that you know instead of trying to memorize all the things that you think are extra. Because they're really not extra, there's just tying in what you already know.
Right.
And if you have the tricks in your head, use them. But I'm trying to stay away from tricks today, because that's the whole goal, is get back to the basics if you have to. I'm always one that goes back to definitions when I need to. Okay, so what's the sign?
Fits.
Negative root 21 over 5. Right, the y value over the radius. What's up, Rosanna?
So you always use the point that's closest to the center, the axis of, well, the center in order to look for the sine, cosine, and tangent?
You always make a triangle with the x-axis.
Right, but to figure out which way you're looking for the sine and the cosine, you gotta be looking at an angle.
Correct.
So, and I'm asking, is it the one that's at the center?
So the answer to that, you're not gonna like it, is yes and no. There's an infinite number of angles that would put me here. Remember the earlier I said I could go around 47 times and then stop? So the specific angle that I started with here, I have no idea what it is. But what we do, the yes part, is that the one we think about is what we call the reference angle, the one that
That's
makes
what-
with the x-axis. But we
Yeah.
don't know for sure that that was the original angle.
Okay, but that's the one that you're using in order to determine the
Yes.
sine, the cosine.
So those people who remember SOHCAHTOA and use SOHCAHTOA, it's referring to that little guy in there. Which I'll talk about SOHCAHTOA a little bit. So we got the sine, we already had the cosine. I'm gonna give tangent. Tangent is negative root 21 over 2, she says. We agree?
Yeah.
Right, the y over the x. Can you guys get the rest of them without me showing you? Look them all over correctly, the right ones? Okay, let's take a little break right here. Let's just take a little 10-minute break. We'll come back, we'll move on, we'll do some other stuff. We're gonna solve some pretty hairy equations. If you came in late, I brought some food and some water, help yourself. By the way, we will not finish everything in this packet, but we'll get through hopefully a lot of it to get you started, and you should be able to finish the other ones. I'm gonna be skipping over some. Wanted to point out one thing. The problem we did just before the break, you guys all had it in your notes, but for those people who are watching the video, the restriction was that beta had to be in the third or fourth quadrant. I just wanted to make sure I wrote that down, pointed it out, so that when people look back later, and how'd she know it was the fourth quadrant? Because without that, a positive x value could have been in the fourth quadrant, or maybe the first quadrant, right? So it turned out we needed that information. Just want to make sure I was being clear. Okay, so I'm flipping over to example 6, and I'm going to skip a couple of them because they're similar to what we were just doing. Example A has an 11 pi over 4. Basically, we need to figure out where that is. Seeing that it's a pi over 4 tells you what? Well, just the pi over 4 part. 45 degrees, right? Which means it's going to be the special triangle that's 1, 1, square root of 2. So it's almost identical to this problem, really. Except we just have to label it with 1s and negative 1s and square roots of 2s in the correct quadrant. So I think you guys can handle that. I want to talk about B though, because all of a sudden the triangle is gone. There's no triangle here. So if you look at B, we need to find negative 5 pi. And we want all the 6 trig functions for negative 5 pi.
You know where pi is.
We know where pi is, and we know which direction is negative. So here we go. Here's negative 1 pi. Negative 2 pi, negative 3 pi, negative 4 pi, negative 5 pi. So I went around a bunch of times, and I ended up here. Right? So here's my point over here. I ended up on the end of this point here. Uh-oh, there's no triangle there whatsoever.
But it's only a unit circle, so it's up to 1, right?
Yeah, you technically can label this any point you want as long as it's on the x-axis. So most people like to use the unit circle, and what would you label this as?
-1.
-1 is the x, and what's the y?
0.
0. If you wanted to be creative and call it -45, 0, you could. You'd still get the right answer also. So here's my x and my y. What's my r? What's the distance from here to here?
1.
R equals 1. Right? R is the distance from the origin to your point. What would have happened if I had gotten creative and called that -45, 0? What would R have been? 45. Would have worked out just fine.
So you're saying it doesn't matter what x would be in this case?
It doesn't matter as long as because your R will match that value. So if x is -pi, then that's pi. Or if it's -√38, then that's positive square root of 38. But by convention, most of us just pick 1 because you're used to the unit circle anyhow. So it's just easier to work with, but technically it could be anything.
So you said it could have been 45?
Sure.
Would,
Picture would have looked like this. -45, 0, and then my R would have been 45. And when we go to do this, none of them would change. I'll show you in a second. Is the picture okay with the x and the y and the r? So now we have to go with the definitions. What's the sign of this angle?
0.
0. It's the 0 over the 1, which is 0. So when somebody walks up to me in the street and says, Jill, what's the sign of -5 pi? All I do is I picture, oh, that's over there on the x-axis, the y value is 0. The answer must be 0. Because I have it in my head, the sign is the y. If I'm on the x-axis, the y value is 0. I don't necessarily know the sign of -5 pi, but I know that it ends up on the x-axis where the y values are 0.
How often do people walk up to you and ask these questions?
There you go. You'd be surprised though. You'd be surprised. Usually people walk up to me and say hi and they were in my class, but they don't usually ask me these questions. You're right. My kids used to go crazy, like, do we go everywhere and people know you, Mom? I'm like, yeah, pretty much. Everywhere. So we're okay, y 0? What is the cosine of 5 pi? -1 over 1, which is -1. So again, when these people hypothetically walk up to me and ask me these questions, I'm picturing, oh, I'm over here on the left side, the x value is negative, so it has to be -1. Yes.
Should the angle that you're writing be -5 pi?
Oh, yes, sorry, I'm not copying that down wrong, thank you. Let's squeeze that in, is that what you were gonna say too?
Yeah.
I had it here. Thank you. Turns out that -5 pi and 5 pi end up in the same spot, so it technically wasn't wrong.
Yeah.
But let's stick with the original one I wrote. -5 pi just goes the other way and ends up stopping right there, so it doesn't technically matter, but you're right, this was the original one.
And then that cosine, Jake was.
If I'm gonna fix it, I should fix it all?
I wasn't gonna say anything, Jake wanted me to say.
No, people on the video, right? If you don't say something, these people watch the video, she doesn't know what she's talking about.
Thanks, Jake.
Yeah, thanks for the video, right? It's all wrong. What's the tangent? 0 over -1, which is 0. Oh, here's where it gets interesting. What's the cosecant?
Undefined.
Undefined, he says, because you cannot divide by 0. It's undefined. Which is why cosecant, if you remember the graph, has these little asymptotes. There's places where it's undefined.
So cosecant and cotangent would be undefined as well?
Yes, cotangent will be undefined as well. Beautiful. So the secant's, again, the reciprocal of -1 is still -1, but he's right, the cotangent will also be undefined because we've got -1 over 0, which is undefined. Gorgeous. So this is where SOHCAHTOA fails, because where's my triangle? How do I know which one's the opposite and the adjacent, right? We can't do any of that, but I can remember X and Y's and go from there. So 9 pi over 2, same thing. First off, where the heck is 9 pi over 2? I thought some of you are thinking in your heads, I can see your little heads going around. Yeah, Rosanna, were you gonna
No,
say? Oh, okay, she's thinking too. You guys are all like counting.
Second quadrant.
Yeah, so it's technically not in a quadrant, so what do you mean by second quadrant?
We know that that is pi over 2,
This is pi over 2.
and then we just count.
So you counted 9 of them?
Yeah.
I like it. 1 pi over 2, 2, 3, 4, 5, 6, 7, 8. Here's 9 pi over 2. So technically it's the edge of the first and the end of the first, beginning of the second quadrant.
What would be your tip for if it was just a huge like pie, like you said?
Look for multiples of 2 pi.
Okay.
So if, let's say the problem happened to be 91 pi over 2. I don't want to count to 91, right? I would have done 90 pi over 2 plus this extra one.
And then.
Well, this is 45 pi, and this is an odd multiple of pi. If it's an odd multiple of pi, it's not going to end up here. Where's it going to end up?
On the other side.
Over here,
Uh-huh.
plus another pi over 2.
Okay.
So just look for multiples of pi. If it's even, you know you're going to stop here and then add something. If it's odd, you're going to end over here and then add something. Good question. Okay. So we want the 6 trig functions for this. We need what?
Point.
Point. What point do you want? Point is that?
1,0.
Oh, you're close. Try again. 0,1. Matters, big time, right? Make sure you get the x and the y straight. 0, 1. So the sine of pi over 2, 9 pi over 2. Oh, what's the r? Uh-oh, I didn't mention the r. How far is it from here to here? 1. R equals 1 here. So the sine is 1 over 1. That's 1. What's the cosine? 0 over 1. Which is 0. What's the tangent? Undefined.
Because there's no tangent line here. Oh, yeah, I mean the tangent line.
1 over 0.
Let's see that. This one.
Squeeze that in there. Undefined. Can you read that one? We see why it's undefined? You guys okay with the other 3? You got it now? So this is why I personally like this definition better than SOHCAHTOA, the opposite and adjacent, because what the heck do you do when you don't even have a triangle? Right? There's no triangle, you're stuck. But if you just remember the y is the sine and the x is the cosine, you can get any point on there and figure out what to do from there. Feeling better about that? Okay, I'm gonna leave the A and the C for you guys to do another time. And I have my problems out of order, I noticed. Before we can do example 7, I have to mention some identities on the next page. So I want to flip over to, I don't have my pages numbered, sorry, where it says a few trig identities. The example 8 up there is more of what we've just been doing also, so I want to move on so we can solve some equations here. So a few trig identities. In the first box in the middle of the page has the 3 trig identities, the first line, that pretty much say the same thing we talked about here. It says that the cosecant is 1 over the sine. 1 over something just means the reciprocal. This cosecant is 1 over this. 1 over y over r. 1 divided by y over r is r over y. It's just a shorthand way of saying that this is the reciprocal of that. The secant is 1 over the cosine. They're reciprocals of each other, basically. And the same with the cotangent. And then there's tangent theta equals sine over cosine. A lot of you already have it memorized because you used it so much. Let's show you why. Let's show you why the tangent is sine over cosine. We're not going to spend a lot of time today proving these identities just because it's going to take too much of our time. So this is the identity. Again, everything in that box, those few trig identities, you will need to have those guys memorized because otherwise, well, you don't have to memorize the first 3 because these actually tell you that. But this one you definitely want to know because it just makes your life easier and switch things around quite a bit. Tangent of theta by definition is the y over the r over the x over the r. Well, if I take this fraction and divide it by that fraction, I flip it over and multiply, I get y over x. So there's these identities that if you can't remember them, they actually come straight from the definitions, those first ones in the box in the middle of the page. The next one's called the Pythagorean identity.
Is that being multiplied?
I'm sorry, this is multiplied right here.
Okay.
Sorry, you got it? Then there's that Pythagorean identity. There are actually 3 Pythagorean identities, that's why there's those 2 blanks next to it. I only have the first one memorized. I'm going to show you how to remember the other 2, how to get the other 2. Those of you in my class, I've shown you a couple times already how to get them. You could show why this is true quite easily by plugging in the definitions if you wanted to. You could do that and it would work. But what I want to do is use that to come up with the other 2 Pythagorean identities, because that's just busy work to check those right now. We don't have all day, unfortunately. So the trick to get the other 2 is to divide by one of the other trig functions. So for example, if I decide to divide everything here by cosine squared, just divide both sides of the equation by cosine squared. What is sine squared over cosine squared? Tangent squared, right? The sine over cosine we just talked about is tangent. So that next line over, tangent squared plus cosine squared over cosine squared is 1. Anything over itself. And then you have to recognize that 1 over the cosine is secant, and it's squared, so it's secant squared. This is the second trig identity. It's on the second line there on your notes. The second Pythagorean identity. I do not have this one memorized. I don't. I have this one memorized, and I know how to get this one. I can't keep it straight, because then I'm like, is it tangent minus 1? Is it secant plus 1? Where's the plus go? I can't remember. I don't want to have to memorize all that, so I just know that I can find it by just dividing everything by cosine. And if you want to find the other ones, you can start with the same thing again. I guess we're going to divide everything by sine squared. Divide everybody by sine squared. So I always tell people they're all the same identity. They're just kind of being rearranged. This is 1 plus, ooh, what's cosine over sine? Cotangent, so that's cotangent squared. And 1 over the sine is
Cosecant.
cosecant.
Do you have a way to memorize the 1 over cosine or 1 over sine? Or you're just doing the r over?
What do you mean the 1 over cosine?
I mean, 1 over cosine squared theta is immediately, I don't see that that's secant squared right after that.
Ah, okay, so when you see 1 over cosine squared here, you want to think of that as what fraction was being squared.
Okay,
So that means I must have been squaring this.
right?
and there's your secant
Okay.
right there.
Right.
So I guess after a while, you learn that squared is kind of like a bigger picture, like the
Right.
whole thing was squared.
Yeah.
So I kind of picture this in my head.
Okay.
That's what you're asking?
Yeah, just trying to see a trick maybe that I can remember that.
Yeah, so when you see anything squared, try to think of it more as what fraction was being squared, if it was the top and the
Yeah, I
bottom.
get that part.
Good question.
Yeah, I get that.
And then down at the bottom of that page is a couple more identities that come up quite often. The one I want to mention right now that we're going to use, I'm going to put it up here in this corner. There's two of them which in calculus show up more often than the other ones. Okay, maybe not the Pythagorean one, it shows up everywhere. For those of you who are in 60, you've already been using this one. There's a lot more identities, but we're just going to use these two for now. If we wanted to prove them, we would just plug in those fractions and do the work and show that it was a true statement. We're not going to prove them right now, but we're going to use them. And we're going to use them to flip back now to example 7 and simplify that messy thing. It takes a while. But this, I'm telling you, is a problem that just came off my calculus homework I was grading. It's not a calculus question by itself. Everybody get these down? Those identities? I put boxes around these because they're the identities. I argue don't memorize them, just know how to get them. If I know I have something with secant squares, I'll divide by cosines and make a secant show up somewhere. That just kind of works better for me than memorizing them all. Okay, so we have this long messy thing here, which is exactly the kind of problem you're going to encounter in Math 50 or Math 60, and you're going to panic because it's got trig in it and say, I don't remember my trig, Jill. That was talking about me in the third person. I mentioned that earlier. So here it is. Theta plus 1/2 sine 2 theta minus 1/2 minus negative 1/2 theta plus sine of 4 theta plus 3/2. So in Math 60, this is like the second to last line of a problem that takes up at least a page, depending on how big you write. So you've done all this hard calculus, you did it all right, and you get to here, and then you're like, oh, I don't remember my trig, what do I do? This is why we're doing this today, right? So we're going to just plug in theta. We're supposed to plug in theta and then simplify it. We'll do it one little piece at a time. So that's going to give me pi over 3 plus 1/2 sine of 2 times pi over 3. That's what 2 theta means, right? In those parentheses. Minus negative 1/2 times pi over 3.
You missed the 1/2.
Oh, thank you. Why I need you guys here. Can you imagine if I was making my own video without you guys here? I'd make all these mistakes and no one would tell me. There we go, thank you. Negative 1/2 times pi over 3 plus sine of 4 times pi over 3 plus 3/2. I think I got them that time. I'm just plugging all the thetas in. Who's still panicking? I swear we have enough tools to do it now. Bless you. Okay, I'm going to simplify a little bit, and then we'll go from there. This is pi over 3. This is 1/2 sine of 2 pi over 3. I'm just going to write it all as one angle now. Right, 2 times pi over 3. Minus 1/2. Minus, this is negative pi over 6. Just multiplying fractions, right? Plus sine of 4 pi over 3. Plus 3/2. What do you think I need to do next?
Distribute.
Distribute.
The negative,
I can distribute the negative right now if I wanted. He wants to take this negative and take it through there.
and then combine right there.
Well, then you have to
combine like terms. Okay, so we need to distribute the negative, I agree. We need to combine like terms. What are you saying?
You need to find out what pi over the.
Yeah, we need to figure out these sign things too. So the order that we do these doesn't technically matter. It's all going to happen. I'm going to do the trig part first, and then we'll simplify things up a bit. So this sine 2 pi over 3, this part right here, and this part right here are what we've just been practicing. Right? So you're stuck on a desert island without a calculator, and if you get this problem right, you get to leave. We now know that we can do it without a calculator, right? So I'm going to draw a picture of 2 pi over 3, which we've done a few times. That's why I gave you those two little things down the bottom of your notes there. 2 pi over 3 we've done a couple times today. It's still over here. What angle is this right here?
30. No, 60 degrees, so 530.
You sure this one's 60? Are we guessing?
That's what it was.
Pi over 3? I'm just making sure that we're confident, that's all. You could be right.
Yeah.
You had some hesitation though. Is it pi over 3 or pi over 6? It's pi over 3. Why?
Because it's the larger.
It's the bigger one, right? The bigger one is the 60 and the smaller one's the 30. You can also tell, even if you don't remember which, oops, pi over 6. If you can't tell, you can at least tell that this is the shorter side, which means this is the 1, and it's actually a negative 1 because we're going left. This is 2, this is square root of 3. So what is the sign of 2 pi over 3? Square root of 3 over 2? The y over the r? So I'm going to put that in right here. Pi over 3 plus 1/2 times square root of 3 over 2 minus 1/2. Now I got to figure out this one. I have to do the side of 4 pi over 3. Where's 4 pi over 3? Third quadrant, because this is pi, or 3 pi over 3. And I have to go 1 more pi over 3, I end up down here-ish. What's this angle right here? She whispered it over here. It's another pi over 3, right? Because we went 4 pi over 3s. One, two, three, 4 pi over 3s. And my sides are going to be labeled -1 because I went left. Hypotenuse is always 2. And negative root 3 because we went down. They're both negative. So what is the sign of this angle? Negative root 3 over 2. That's got a negative y this time. Again, I can't tell you enough that I do not know the sign of 4 pi over 3. But what I do when I have to figure out, I either grab a piece of scratch paper, or actually what I do now is I kind of draw this little thing in my head. Like, oh, 4 pi over 3, that's in the third quadrant. The sign is the longer side, the y is the longer side, and I'm actually visualize this triangle in my head. It's got the longer, so that's going to be negative. That's the negative root 3 over 2. I always ask myself, is that the short side or the long side? Go from there. So now that we have the trig filled in, now we just need to do some combining and simplifying. I'm going to multiply here. Pi over 3 plus square root of 3 over 4 minus 1/2. I'm going to distribute the negative sign on this other one while I'll always take these parentheses off now. They're not really needed if there's nothing in front. So I'll take those parentheses off. I'm going to distribute these parentheses. That's positive pi over 6, positive square root of 3 over 2, negative 3 over 2. Did I lose any signs? Think I'm okay? Okay, so we need to combine some like terms. That's fun. Nothing looks real pretty here. Oh, maybe these little fractions are good. I can combine these guys easily. -1/2 and -3/2. Or -4/2. So those give me a -2. But what do I have to do for the other guys? Yeah, I need a common denominator. Life just got messier. We can do it. So combining these fractions that have pi in them, I'm gonna do those first. Common denominator is 6. So 2π/6 is what I get here, multiplying top and bottom by 2, plus another π/6. Am I okay with the 2π/6 came from? Combining the square root of 3, guys, grab another color. Combining these, common denominator is 4. So I need to multiply this one by 2/2. So I have, so I'll leave the green up here so we don't get confused. The first one can stay, it already has the 4, but the next one is plus, 2 square root of 3/4. So I multiply top and bottom by 2. And then finally, the last one is just -1/2 minus 3/2. I just rearranged my terms to put the like ones together and get common denominators. It's all algebra, unfortunately. When I combine these, I get 3π/6. Yeah? Plus 1 plus 2, 3 square root of 3/4 minus 4/2. And so finally, the only thing I can do now is simplify this, which is just π/2. This is just ugly, it doesn't reduce. And there's a 2 right there. Whoa, she says. But think about it, okay, so she says, wow. You have a question?
Yeah, I was gonna ask you, so what did you do with the 2 square root 3/4?
I added this 1 square root of 3 to this 2 square root of 3.
Oh,
We got 3 square root of 3. So this problem is like, wow, and overwhelming and what a mess. But my point is, yeah, it's messy and it's long, but you can do every little piece. Just accept that sometimes life is long and messy, but as long as you can do every piece, you'll get there. It's when, I mean, the reason we're here today is there's people who get here and they see this and they're just like, I can't do this, forget it. So my point here today is I'm trying to give you the tools that not only can you fill in those gaps, but you can just take your time and do every little bit. Calculus is messy, we just eventually accept it and stop whining about it. Sometimes we do whine about it, it depends on the day. Okay, last thing I want to do today is solve some equations, because that also comes up all over Calc 1 and Calc 2. So I actually want to flip all the way over to example 9, which is my second to last page. It's the last page, but not the back. Example 9, there's like A through G problems right there. We'll start off with the easy one, she says in air quotes, easy one, and jump to some of the harder ones. And I think what I'll have you end up doing is I'll have to get the answers for all the other ones and share them with you later. We won't have time to do them all. So example 9a. This is kind of working backwards where people start to freeze up. 2 cosine x minus 1 equals 0. The directions are to find all the values of x in between 0 and 2π, so you don't need to keep going around and get an infinite number of answers. Find all the angles that make this true within 1 revolution. So the x has to be between 0 and 2π. I'm going to write that down. We don't have my notes. Solve this for x. Because x is inside this cosine function, x is an angle. It's really asking me what angle makes this true. So, what do you think I should do?
Get a cosine by itself.
Get the cosine by itself. Get the trig function by itself. So I'm going to add 1, divide by 2. I'm here. So this is asking me what angle has a cosine of 1/2. As soon as I see that 1/2, that should tell me to think of which special triangle?
30, 60, 90.
The 30, 60, 90, because it has the 1s and the 2s in it, right? So I'm going to kind of now just draw where the heck would I be if I have a x of 1 and an r of 2, right? The x value and the radius. Would the x be the long side or the short side? One's the short side, so I know I have to kind of have the taller one here, where this is 1 and this is 2, and that's square root of 3. See how I knew how to draw it there? My cosine had to be, if the short one was 1 and then 2. What angle is this? Pi over 3. That pi over 3's been everywhere today. We agree that's pi over 3? So, which angle has a cosine equal to 1/2? Pi over 3. But there's another answer. Notice the direction said find all values of x that work. Could I have drawn this triangle somewhere else? Fourth quadrant, he says. Because in the fourth quadrant, the x is still positive 1, the y is negative. But isn't it still true that the cosine is positive 1 over 2? Ooh, what angle is this? What angle takes me to here?
Negative pi over 3.
Okay, so he wants to say negative pi over 3. I like it. Except it doesn't follow my directions, darn it. But we agree with the negative pi over 3, at least for thinking about it. If we go down pi over 3. So instead of going down pi over 3, I'm going to go around once and then back up by pi over 3. So I'm actually going to go around to 2 pi and then back up by pi over 3. So he's got 5 pi over 3, because if we get a common denominator, it's 5 pi over 3. And I actually do the same thing as you, Derek. I think of it as negative, and I'm like, wait, I have to make it positive, so I'll go around again, and then it'll be positive. So these are the two angles that have a cosine that's equal to 1/2. See how to solve that? For those of you who are in 60, when you get to chapter 10, you're going to be doing this all the time. All the time. You're going to need to get multiple answers. They're going to be bounds for integrals that you'll set up. It'll be great fun. Okay, I'm going to jump to one of the little bit more challenging ones here. Same idea as that, but it gets a little bit more complicated. So let's choose, pick a nice messy one. Let's choose E. I like E. 9E. Same directions, but this is now a lot clearer. You want to solve that one. Why is it uglier? Yeah, I've got that sine 2x. Not only do I have sines and cosines in this problem, but I have a sine of 2x, which, by the way, quite often when you read them, those parentheses aren't there, but they are always implied. The 2x is inside the sine function.
Yeah, I have a question.
Yes.
Is that 2 multiplying sine cosine?
This one?
Not the other one.
Which one are you
Yeah,
talking
yeah,
about?
that one, but like,
This one or this one? I-
that one, but like, the 2 sine of x, cosine of x, is the 2 multiplying both sine and cosine?
You're talking about this two?
Yeah.
Okay, that's too many twos. So this is 2 times the sine x times the cosine x. So it's not multiplying both, it's just multiplying all 3 of them. It's kind of like if I asked you to multiply 2 times 3 times 5.
Yeah.
It's not this times this and this times that, just multiply them all.
Okay.
Okay? We're going to have to use that here in a second. But we need that identity here, since he asked about it. Do you agree that if we had the sign 2x, we can use that identity to at least get rid of the 2x's? So whenever you have those double angles, you want to get rid of them. So I have 2 cosine x plus 2 sine x cosine x, using that same identity he just asked about. I just replaced this guy with the identity. And I'm trying to solve this. That's one of the tricks you learned in algebra when you had things equal to 0. One of the nice ways to solve.
Just break that into.
I didn't hear you, Simile?
Put it on the other side, put it on the bottom of the other side.
Put it on the side doesn't usually help. The 0 actually can help us do something else. What were you saying, Joe?
I was gonna say break it up into parts, if both parts equal 0, or?
Okay, break it up into parts. I need more specific
Factor.
words. Factor, is that what you said? Yeah, factoring. So whenever you have things equal to 0, you can factor it and then set each factor equal to 0, which is probably what you meant. We just need to be clear. So a lot of times you want to force it to be 0 and then factor. So what can I factor out here? A 2 and a cosine x. And that leaves me with 1 plus sine x equals 0. And once we factor, we just set each factor equal to 0, because the only way you can multiply two things and get 0 is if either this one equals 0 or this one equals 0. Agreed? I'll divide both sides by 2 here. Cosine x equals 0. Or, I'm going to subtract 1 over here. Always isolating the trig function by itself. So we're panicking. Oh, there's more trig. We don't think we're confident yet. But as long as you remember that the cosine is talking about the x and the sine is talking about the y, you're going to be okay. So if I'm trying to solve this, cosine equal to 0, it's asking me where is the x equal to 0? Because the x over r is the only reason I would get a 0. So where am I if the x values are 0?
You're at the top.
Either at the top, there's an x value 0 up here, or at the bottom, down here. We agree? Because cosine, if you have those little things memorized, cosine's the x. The x has to be 0, so what angles are those?
Over 2.
Pi over 2 is the top one, and 3 pi over 2. 1, 2, 3 pi over 2. This one says, where is the sine equal to -1? The sine is the y value, so it's asking me where am I, if, be careful, if the y is -1. I got people doing this.
3 pi halves.
This is the only point where the sine is -1. You were thinking of x, going backwards. We agree this is the only point where the y is -1? Which coincidentally also is 3 pi over 2. So the answer to this whole problem is x equals pi over 2 and 3 pi over 2. If this one was different, all three of them would be answers to it, but it happens to be the same. So in this case, this is the answer. These are the angles that make this a true statement. And for fun, you can plug them in and check, see if it works. And Jacob didn't think it's fun. How are we feeling? A little bit better? We can do one more of these. We technically could be done now. It's 10 till. Most of us are being done now. But if you want me to do one more of these, I will. You guys want one more? Yeah. Sure, let's do one more. Because the solving ones are the harder ones, I think. Let me pick an even uglier one then. Let's do the last one, G. Let's do G. I have, oops, I just erased my identities, darn it, you guys will have to remind me what they are. 3 cosine x. do I do?
Replace your cosine 2x.
Replace my cosine 2x with my identity? By the way, if you ever look, like in a trig book, or if you have like a reference sheet that has the identities, there's multiple identities that go with cosine 2x. And sometimes you just pick the one that works best for you. In this case, I only gave you one today, so we'll use that one, and the other ones, you're gonna get to there anyhow. So the one I gave you says that I can replace this with,
Cosine squared x.
X minus sine squared x.
okay, so I replaced it, and I just made this equation look worse. So I picked this one. Now it looks worse. So I can't factor it. Why not?
No, like,
Yeah, there's no common factors, so what am I gonna factor out? There's nothing in common. What else makes it a mess besides the fact that I can't factor it? What'd you say? Yeah, the plus 2 might be an issue. There's something else that kind of makes it.
Oh,
Or you have squares on one side and the other one.
I've got a couple different squares and some that aren't squares. What were you saying,
I
Joe?
was just saying exponents.
Exponents, and I see that I have cosines and sines in the same problem. I sure wish I could maybe just change this sine squared in terms of cosine, because then at least everything would be cosines.
1 plus cosine squared.
We know the Pythagorean identity, right? The Pythagorean one that I erased earlier was sine squared plus cosine squared. I'm getting sloppy because we're running out of time. So I can solve for sine squared, it'd be 1 minus cosine squared. See that? We do that identity a lot. So I'm going to replace my sine squared very carefully with parentheses around, oops, it's an x, not a theta. They do that to us all the time, change variables on us. I just made that replacement there using the Pythagorean identity. I agree, it looks even uglier now. But we're gonna distribute and clean up, and the reason I think it's better is at least now we only have one trig function to deal with instead of 2. So let's see what we got. Minus 1 plus cosine squared equals 3 cosine x.
Do you want the cosines together?
Yeah, listen, I like terms. I like it. So I have 2 cosine squareds now. These two add up to plus 1 and 3 cosine x. So your Virgil doesn't look any better.
Wait, I'm trying to figure out what you just added.
Cosine squared plus cosine squared. It's 2 cosine squared.
Oh, that's 2, but where's the other 2? That's what I was looking for.
Which other 2?
The 2 in the front, 2 plus.
2 plus negative 1.
Oh, okay, that's
And
what I was
Okay,
missing.
good. So these 2 together gave me this, and the 2 minus 1 gave me this. Okay, good. So now I'm kind of stuck. It'd be nice to factor. What were you gonna say, Caitlin?
You put the 2 cosine squared x on the other side, and then you can factor out a cosine.
Actually, I want to put everything on one side and have a 0, because just like this problem over here, the reason it worked so nicely is we factored it and had it equal to 0. That 0 product property only works if you have 0 on one side. So I like what both of you were saying. I'm going to put them together. I'm going to put everything on one side and have it equal to 0 and then factor. So I'm going to subtract this 3 cosine x from both sides. And I'm going to put it in the middle to put these in decreasing order. Agree that's the same equation? A lot of people don't recognize this as a quadratic, but imagine if I asked you to solve 2a squared minus 3a plus 1 equals 0. You could factor it, right? Some of you are better at factoring than others, but you could factor it, set it equal to 0. See how you recognize that more up here? That's really the same thing, but instead of a, I have cosine x. See how it's the same thing? So if I factor this, let me bring it up higher so you guys in the back can see it. Yeah, in addition to having to remember all your trig, you have to remember all your algebra too. Right? Algebra also, not just algebra. So I need to factor this. The guess and check method is actually still one of my favorite methods for factoring. The two things I put here and here have to multiply out to be that. So the only options I have are a 2 cosine and a 1 cosine. Whichever one goes where doesn't matter, but 2 cosine times cosine will give me this. I now need two numbers that multiply out to be +1. My only options are 1 and 1. But then I look here to decide what to do with the signs. Since this has to come out negative, that means I must need -1 and -1. -1 times -1 still gives me +1. And if you did a little FOIL, these two definitely give me that. These two give me that. If you check the outsides, that's -2x. This is -1x. They add up to -3x. Guess and check, one of my favorite methods still. So we have it factored. We have it equal to 0. What do I do?
Set both of those into the-
Set both of those equal to 0. So 2 cosine x minus 1 equals 0, or cosine x minus 1 equals 0. Now we're back to what we did earlier. This is the exact same problem we did earlier. It's the exact same one we solved earlier. I think it was the very first one we did, right? Example A. There it is. Did that one already? So the answer to this one, I'm not going to do it again, is pi/3 and 5 pi/3. What's the answer to that one?
0.
0?
It's just 1, isn't it?
1? This is saying what angle has a cosine of 1?
0.
0 is one of them. Is there another one? 2 pi, but remember our directions were not to go, just to stay within one revolution. Let me talk about it. Took a little picture.
So those two, what's the, 2 pi for the parentheses?
Yeah, this means everything starting at 0, going to 2 pi, but not all the way there. So
Oh.
that's staying within one revolution. So technically, the only place where the x value is 1 is right here. So the angle is 0. You won't get there again until you get to 2 pi, but now we're outside of our range. So 0 is the only answer. X equals 0. So the answer to the whole problem is all three of these. pi/3, 5 pi/3, and 0. Any of those angles will make the original problem, which I've now erased, a true statement. How are we doing? Every problem you get, one second, go, takes you back to either figure out which axis you're on and where, positive, negative, or you've got a 30, 60, 90, or a 45, 45, 90, and you should be able to figure it out from there. Every problem. And the more you do it, the quicker you'll get at it. You got a question, Jeff?
Yeah, so I drew I'm looking back for how you got
These two?
cosine x of 1/2, yeah. And then I drew my triangle and I have all my parts labeled 1, 2, √3, and my angle is pi/3,
Mm-hmm.
pi/6. And then in order to get the pi/3 part, you're just looking at the angle at the origin, right?
The angle that it makes with the x-axis,
Okay.
yes, always.
Okay.
We didn't do any examples where our triangle looked this way, where this was the 1, the 2, the square, and the 3.
Right.
The only thing that would change is my angle here would now be the pi/6 instead of the pi/3. It turned out that on my examples I picked out pi/3 today.
And that would be like an example of sine, or
Yeah, like if we were trying to solve sine x equals 1/2,
that'd be that one. Okay.
that'd be this one. See it?
Mhm.
We good? Okay, that's as far as we're getting today. I had more just in case we had time. I should have known we wouldn't. So we're good for today. If need be, I may do another one later, but I think now you actually have enough tools to do everything on that handout I gave you. The graphs I just gave you for reference if we had time to talk about it. I recommend you try to do all the problems we didn't do today to see if you can. You'll feel more confident and stronger with your ability to do that. I'll get all the answers to and give them all the instructors to share with you guys as well and put them in the math book. Yes?
Are the graphs on the back for reference, or is that another?
They were just there because I wasn't sure how much time to allot for our discussion, so if we had managed to get through everything else, I was gonna take what we had to show you how what we just talked about could be, graphs, if you don't have those memorized as well.
I might
Take the